Okay, good afternoon. So we're going to start the first tutorial with Chris. So you know me, I was teaching yesterday. My name is Roman. And I'm the main author of this code, Ramses. And Ramses is an acronym. It means adaptive mesh refinement without too much effort, but in French. So it's a French acronym. Nothing to do with the Egyptian king. And I will basically describe this markdown pages and live do the demo of this tutorial. But you have access to this GitHub page, the same page as yesterday, and you can really do it yourself if you want and advance at your own pace. Right? You don't have to wait for me. I guess there are some different level of, use of this kind of code. So feel free to go faster if you want. And so I will slowly explain for those of you who need more time. And the goal is to basically use 1 hour and a half for Ramses, and then Chris will take over and use the remaining 1 hour and a half to present the Athena tutorial.
We'll give you a coffee break or something.
Yeah, so that's a tutorial. So we you can walk out of the room and it's like no stress. Right? Okay, so let's go. So the first thing you need to be able to do right now is to connect to Rusty. So in principle, you should have all the information. So I know that there is 2 options to connect to Rusty. One is to use Jupyter Hub. The other one is to use your own terminal window on your own laptop. Right? So it's up to you, no preference. Okay, so first thing we're going to do is we're going to connect to Rusty. So please do it together with me. So here, that's a very broad, description of what you need to do in order to have a terminal window on your laptop if you want to use the terminal window option. Otherwise, just use Jupyter Hub as it was explained to you yesterday and connect using your web browser. Right? In both cases, you need to end up in a terminal window. Right? So that's a terminal window. Right? And so you need to land on Rusty inside the terminal window. Right? So you can use either Jupyter Hub or directly your own laptop terminal window. Okay, so who's in trouble to do that? Nobody? Great. Okay, great. So then you can bypass most of this first page. So here I have a basic dictionary of basic Linux commands for those of you who are not familiar with Linux. I hope you are. Okay, so now the second very important step is to set up the Rusty environment. So I know that you have been explained how to do that yesterday, but I'm going to repeat. The key point for for all the codes that you're going to discover this week and next week, you need a compiler, and you need, most of the time, additional libraries that this code needs to compile with. Okay, and so everything is available on Rusty through the module command, which allows you to manage packages. Okay, and so if you type on your terminal window module avail, you should see all this list of modules, right, or packages. And here you can see the first block here. Those are the most used modules, and they have actually a shortcut name, like an alias. Right? For example, just to show you 2 examples that we're going to use a lot. Okay, let me show you on my terminal window. So if you type module avail, okay, so you have these aliases. And the one we're going to use a lot here is OpenMPI, which is the MPI library to perform parallel computations. And also, we're going to use Python. Okay, so those 2 are the 2 packages that you need to load in your environment in order to be able to compile the code. We're going to do in a minute, right? So in order to load the module, I mean, again, most of you probably know how to do that, but you have to first check what modules are already loaded in your environment. So if you type module list, it shows you the modules that are already loaded in environment. So I don't know why. I mean, I have 3 modules already loaded, right? Except none of them are going to be very useful for me, right? So I don't know, what do you have? You have also the same 3 models? Okay, great. So I guess that's the basic modules that everyone should have. So now in order to load MPI, you have to type module load, and then open MPI4, which is the alias, the shortcut. Right, module load, open MPI4. Boom. Right. So now let's have a look at, again, by typing module list. And now you see there is a new module here, OpenMPI 4.0.7. Okay, remember that the name of the module is this one. Right? OpenMPI 4 is just an alias. Okay, so now if you want to remove this module because it interferes with whatever you have, then you type module unload OpenMPI. Not OpenMPI 4, OpenMPI, right? Because that's the name of the module. Okay, and so if you do that, you check what's happening, right? Module list. Now you see that it's not there anymore. Okay, and so for those of you who are familiar with module, don't listen to me. For those of you who are not familiar with module, what module does is that it loads all the environment that you need to have set up on your account so that OpenMPI will work. In particular, it provides links to the libraries. And you can see what happens if you type echo $library path, which is an environment variable, contains all these links towards libraries, right? Open Blast, share, whatever, but nothing for OpenMPI, right? So now if you type module load OpenMPI 4, and now you look at this new library. Now it has new libraries. Right? This one is new. Right? Okay, so now your environment has been set so that it knows where the library for OpenMPI is, and okay, so that's the magic of this module load and module command, right? Okay, so now we need to also load Python. So again, Python 3. So now we should have 5 packages now, and those 2 are the ones we're going to use mostly. Okay, easy. So now your environment is completely set up on Rust. Okay, so if you don't want, so be careful, each time you log out, this is gone, right? The modules are gone. So each time you log in, you have to do module load again, right? Which can be a bit annoying. And so if you want to avoid doing this each time you log in on Rusty, you just have to put this 2 commands, module load OpenMPI 4, module load Python 3 in your .bashrc file. Right? And then it will do it automatically. But you might as well also not do that, right? You want to avoid having these modules preloaded, right? That's up to you. Okay, now second step, let's get the code. So the idea is to use here something which is called a software management tool or a version control tool, which is Git. So Git is a very nice software that probably you already know, but for those of you who don't know Git, it's actually a command that you can type on the terminal window that allows you to control the different version of your code, or it can be a document, a paper, a report, whatever. So you can work collaboratively and update this unique product in a server, usually an open source server. In this case, it's Bitbucket. It can be Bitbucket or GitHub. And you can work collaboratively, modify the code, taking care of the different versions, and so on and so forth. And so what I ask you to do, so let me show you how it looks. So you have to go to the Bitbucket website. So that's the Bitbucket website. And then if you type the address RTCA, that's me, /Ramses, then you're going to land on the Ramses Bitbucket page, which is this server, this centralized server that contains the last up-to-date version of the code. And you can see, by the way, all the work that has been done on the code by looking at the commit, and you see all the people who contributed to change something, to fix a bug, all the way back to years back. You can see, and what's great here is that you can really identify bugs and you can blame the person. So it's really good. So now, in order to clone, that's how we call it, to clone the code on Rusty, you just have to type. Let's go back. So you have to type this command, git clone, then this address here, https bitbucket.org rtc Ramses. So if you type that, it will load the Ramses repository on Rusty from the Bitbucket site. So anyone having problem doing that? So you should see like a percentage kind of a thing. Okay, great. So there is a lot of if you want to become an expert of Git, you can follow those resources here. But for us, we just need Git to download the code, right? Okay. So now let's see what we get. So you should have like a Ramses repository, and so if you go inside Ramses, you have a whole bunch of. Okay. Let me clean a little bit my. You have a whole bunch of directories, right? And those directories, they contain the source code, they contain various, scripts, utilities, whatever. So, okay. So the first thing we're going to do, we're going to compile the code, and for this, we're going to use a technique called the makefile. Right? So makefile, it's like a programming language to compile codes. Right? So the code itself is in Fortran, but you don't really need to worry about this. The thing we're going to use now is the makefile. So before we do the theory of makefiles, let's just compile the code. Right? So for this, you go into the bin directory, which should be empty. Right. So it should be completely empty. So let me remove all the junk here. There we go. So it should look like that. It should contain a makefile. Right? Okay. And so here you can type make, just make, and something like that should happen. Okay. So this is compiling, right? So anybody has trouble at this stage? Okay. So what it does, for those of you who are not experts in compilers, what it does is that the compiler, in this case G-Fortran, compiles all the source files, turn them into objects, which are like machine language, files, and those objects, they all end with .o at the end, like object, .o. And you have plenty of objects. Each file is turned into an object, and those objects are functions that execute a function in the code. And then at the end, what you do is you link all those objects into an executable, which is this guy here, Ramses1D, which is actually the executable that you're going to execute on the machine. Okay. And so there is these two steps: compilation of objects and then linking into an executable that the compiler is producing. Right? There is actually a third step that usually we do before the compilation, which is called the preprocessor. The preprocessor will actually analyze your code, try to find some preprocessor directives inside the code, and replace those directives by some value you give them. For example, I give you an example. If you type make ndim equal 1, it means that I tell the preprocessor that this variable, ndim, which is the number of dimensions, has to be set to 1. Right? And so it will look inside the source files everywhere for this string, ndim, and replace it by 1. So it's editing your files into new files. And then those new files are sent to the compiler and to the linker. So the preprocessor is really a first step that you do before. So these are the 3 steps of the compilation: preprocessing, compilation, and linking. Okay, so this is all done by the makefile. Okay, so I mean, you can have a look at the makefile also if you're brave enough. And so it's a big file, right? As I said, it's a programming language for compilation, right? And so you see all the preprocessor variables are listed here, right? And those are the default value, but you can change those, like I just did. Right? And we're going to do it in a minute. So you see, you can use turbulence, you can use radiative transfer, you can choose the solver, hydro, MHD, whatever. You can change the number of dimensions, 1, 2, or 3, right, etc. These are all the preprocessor directives that you can change yourself, right? Then, okay, let me skip this. It's probably not important. Then you have 2 options for the compiler. You can use the GNU compiler, G-Fortran, that's what we did. But if you prefer, you can use also the Intel compiler. Right? So there's 2 options. Okay, so usually the Intel compiler is faster on Intel products, right? It's kind of obvious. And then that's the compilation of the libraries. So if you need those libraries, right, or not, and then all the objects. These are all the objects that the code will compile. And then at the end, it will link all the objects into the executable. And so these are all makefile kind of programming syntax that you don't have to worry about. Okay, that's the makefile. Okay, so now in principle, you must have produced this executable, Ramses 1D. Yep.
Sure, quick question. Is it possible to parallelize the compilation?
Later.
Okay.
Oh, parallelize the compilation.
The compilation, yes.
That's possible. I know it's possible. I don't know how to do it right now.
Okay.
You can.
Yeah, I tried dash J, but I got
it didn't quite work.
Okay.
Yeah, it depends on how the makefile is written and how the code is structured.
Okay. Yeah.
So sometimes yes, sometimes no.
Okay.
And if you're logged into just one core through like Jupyter Hub, it won't speed up anything anyway.
Yeah. Okay, so now we have compiled the Ramses 1D. So let's now go back up one level and let's run the code to see what comes out. Right. So let me make sure that I'm following the structure here. Yeah, that's the makefile we just described. Make. Okay. So that's here. You can see here. That's another example to compile with MPI and with 2 dimensions instead of 1. Right. So we can do that. We can do that right now before running the code. So let's do this. So then you need to go back to bin. So now, very important. If you change very important preprocessing parameters like the number of dimensions, you need to make clean. Always make clean. If you have a doubt, just make clean. Right? It removes everything, and then you compile fresh. Right? So let's do make clean. And now, no, not clean. And now it should be completely gone, except the previous executable is still there. Right? You don't want to recompile. Right? So Ramses 1D is there. You don't touch it. But now we're going to create a new executable. So now you have to do make ndim equal 2 and MPI equal 1, because we want to compute with MPI. So remember that you need to have module load OpenMPI 4. Otherwise, it won't work. There we go. So now you see the compiler has changed. Now it's MPI F90. It's not G-Fortran. It's compiling with ndim equal 2. You can see it here. maybe we are all of us compiling together, so that's why it's a bit slow. The same thing, so it's a bit silly. Okay, almost there. There we go. So now Ramses 2D, that's the new executable, right? And so now we have two executable, Ramses 1D, Ramses 2D. Okay, and Ramses 2D, be careful, it was compiled with MPI, meaning that now you have to run it in parallel, this one. Ramses 1D, no. Ramses 1D was compiled without MPI, so we can run it in a serial mode. Right? Okay, great. So as you can see here from the page, these are the pre-processing directives that you might want to use in most cases. So ndim, 1, 2, or 3, MPI, 0 or 1, compiler, GNU or Intel, and debug, 0 or 1. Right? Debug equal 1, it activates all the debugging option of the compiler, so the code will be very slow, but it will check for any overflow, divide by 0, it will hunt for all this weird stuff. There are other preprocessor directives inside the makefile. Feel free to explore them, but those are the main ones. Okay, now let's run the code. So, okay, so the idea now is to first run this first example, which is the SOD test that I showed yesterday, right? So we're going to run so Ramses 1D. So here you have to go up one directory. So let me do it. So we cd ... So now you're here, right? And now let me clean this output. So it should look like that, right? I mean, almost. Still have some few. Okay, now we're going to run the code. So remember, this is not compiled with MPI, so we can just execute the executable directly, right? And the only thing that the code needs is a parameter file to know what to do. Okay, and so this parameter file are all in the namelist directory. So you type Ramses 1D bin / Ramses 1D, that's the executable. And then in the namelist directory, there is a whole bunch of example of parameter files. We're going to use the one called tube 1D, which contains the SOD test, the shock tube test that I presented yesterday. So if you just type return, boom, it runs. Okay, and so so there's a lot of information that are outputted to the standard output, the terminal window. And actually, if you go back up, you run out of space in your terminal window. So actually, it's probably better to redirect this using this greater sign into a file, right? Into what we call the log file. Let's call it run.log. And then it will run and dump everything, not to screen this time, but inside the file run.log. And now you can peacefully look at this file from the beginning, right? And so you see, so it tells you nproc equal 1, ndim equal 1, and number variable 3, that's density, velocity, pressure, right? The 3 variables. The compilation date, blah, blah, blah. And then it gives you the initial AMR structure. So now Ramses is an AMR code. So it has levels of refinement. And by definition, level 1, it's one grid covering the entire box. Right. So there is one grid, level 1. At level 2, there is 2 grids because we're in 1D. So we have 2 grids. Level 3 was 4 grids, so on and so forth. And then after level 4, we are not, we should have 16, 32, blah, blah, but no, because we refine actually only the initial discontinuity. Remember, it's a Riemann problem. We have 2 piecewise constant states with a discontinuity in the middle, and the code refines the discontinuity. We're going to see that in a minute. Okay, so that's the initial condition here, all the way down to level 10, right? So we have here an effective resolution of 1024 cells, but we only have 100 cells. We need only 100 cells carefully located, close to the discontinuity, adaptively refined, to get an effective resolution of 1024 cells. right? So that's the beauty of AMR. You only put your computational resources at the strategic location, which is in this case the discontinuity. And so there's only 58 cells, actually, only 58 cells out of possibly 1024 if you have a fully refined grid. So the gain here is huge. Right? It's a factor of 20. Right? Okay. So that's the initial profile. So you have the level of refinement, the coordinate of the cell. So these are big cells, and then they becomes progressively smaller and smaller. This is the density, the velocity, and the pressure of this initial problem that we are setting here. And you can see here the finest cells here, which are precisely where the density jumps between 1 and 1/8. So those fine cells are on top of the discontinuity. Right? And then now we do the time integration. So this is now you see the time steps that are progressing. Right? So the time integration is progressing here. Okay, so just to show you this interesting aspect here that Ramses has adaptive time stepping, meaning that you have a main time step, which is very large, and you have a fine time step, which corresponds to the finest level, which is very small. So we have adaptive time stepping. So we have also AMR in time, right, to also avoid updating too frequently cells that don't need to update frequently because they're huge. Right? Okay. Okay, so and then okay, and now that's the final time, right? So we reach the final time. We have 142 cells, and now you see the profile here that we're going to visualize in a minute, and that's it. And it's finished, right? And it tells you where you spent some time and whatever. Okay, that's the first kind. So everything works for everyone. No bug, no weird stuff. Okay, great. So now, okay, so now let's try to visualize this. So for this, there is multiple options. I propose we start using Python. So what you can do, following what you were taught yesterday, is you can open a Jupyter notebook on Rusty. So are you okay with opening a Jupyter notebook on Rusty? Let me know if you have trouble. Otherwise, once you have opened your notebook, just try to copy paste from this page those 4 cells. Right? And then you should see this. You should see this density profile, which is the final, solution of this simulation that we just run. Right? So let me know if you're in trouble. So let me do it also. So I need to follow. Oops. Okay, that's how I connect Jupyter Notebook.
Oh, yeah, yeah. I have to add
Oh, so you chimed up so quickly, I was hoping you had a solution. Yeah, so this first
What? Ah, yes, I know it. I am struggling.
Just trying to do the. There's no reason it has to be /10.
So, yeah, me too.
Okay, we're just gonna have permissions in I
Oh, so maybe you should change this then. Remove the TMP.
and just have it to be the run.log.
Yeah, out.txt. Just use out.txt. Maybe you don't have to access, and then you have to change these two.
Oh, right, thank
Yeah, I think that works.
Yeah.
you.
Run.tog is not here. So are you sure you're in the right directory?
I can double check.
So if you type, for example, add a this. No, you need to go inside Ramses.
Thank you.
But you can add if you want Ramses / run.log.
Beautiful, thank you so much.
It just means you have a little bit of clutter that is kind of So I put the absolute platform temporary text files. You don't have to. Oh, you're just jumping straight to it. Yeah. Sure. Just yeah. Just a dot instead of. Unless they think, oh, it could be. Anyways, yeah, I put the absolute dot. Exactly. I did that. But I did basically.
I wasn't.
Dot slash.
Yeah, no. So I think there is so that is something I didn't check, of course. You have to remove /tmp/ because for some reason on Rusty we don't have access to the /tmp directory. So just remove /tmp and put it there.
Oh, I just need to change that again. Wait, do we even need Right, but then the next line,
I know that's what I just said. I'm also.
I just like, I don't know why.
Absolute path again. That's not gonna work.
But then the first, I don't know what the first.
The first step.
Oh.
Yeah, first step.
Yeah.
I want, did you try it with the alpha file as well? The alpha also goes to that. And maybe it has less. Yeah, change the absolute path. I mean, you don't have to, I'm just curious. Too much in spread. Yeah, okay. There's a pretty picture.
We don't.
I mean, oh yeah.
I don't think so. Because I just did this. It just would not. Right, but when I tried to read out of text, it gives me this warning that I didn't have to delimit.
So do you see the plot or? Because I don't.
I gotta do the.
Ah, okay. So what's happening?
Oh, I just did the output. Yeah, that's fine.
Yeah, so this is the output name of the log file.
Okay, I can do
Okay.
it. I don't know if this is right.
Did it work for you?
Ah, yeah.
Yeah, it might be directory. Which directory?
Yeah, you need to make sure you're in the right location.
Ah, that was mine.
So now this should just load out.
So it's weird. I don't see the plot coming out.
I kept, I'm
You
definitely.
tried that too. Where are you typing?
I'm just seeing what is like where I am. I mean, yeah, but I just like want to. Then it doesn't make this obviously, I guess. Well,
Because mine is being run up.
Anyway.
Yeah.
inconsistent table.
Yeah, I like.
Wait, did I read it?
Sometimes you gotta break it to fix it.
I didn't get a table. Maybe it's.
Try the interactive.
Still doesn't like
Nominations, yes. You had to put absolute dots. Okay, yeah.
Oh, I haven't tried that.
Okay. Who's in trouble? Like me, I am in trouble, but who's in trouble?
Should we try the
Yeah.
But should we try the next step?
Yeah, sure. Go ahead.
You said it was supposed to plot something.
The GNU plot. Ah, okay. I'm not there yet. Ah, okay. Oh, come on.
Yeah.
Okay, so let's move to the next exercise then. Okay, so here we are using another software that's, I hope, but it should be available, yes, on the system, which is GNUplot. So GNUplot is a very hardcore, low-level kind of plotting routine, right? Which doesn't have much use unless you use it the way I'm going to show you, which is to use it on the command line to directly generate an image on the command line. Right? So that's really the main added value of GNUplot, is that you can really use it in a script, in a bash script, to produce images automatically using the Linux system. So you can use it interactively, like here. Right? So I am inside GNUplot and I have a prompt. And so the way it's done here, it's a bit like Python, right? But like a primitive one. So you just have to use this example here. And of course, nothing will happen. There we go. In my case, you can see this window that pops up. Right?
No, it's not. Sorry. That's not working.
I probably know why. But so this, you see, that's the initial condition. So you see the initial discontinuity, right, with the very small cells down there, right? And now let me finish, because now I can do something you can't do. Yes. I will show you, I will overplot the final density profile using this command here. And now you see in green, it's overplotting the final density. Okay. So what I'm doing here, I'm using the terminal window on my laptop. I'm connecting to Rusty from my laptop. And I am also passing the display, the X display. That's why I can launch graphical windows from Rusty, like this one, back to my laptop. Right? So you can go to the wiki page of the CCA. They explain how to do that, right? But you don't need to do it. Why? Because you can also use GNUplot the way I'm going to show you now, which is directly on the command line, right? So let me show you. So if you go back to, so that's the example. So here, basically, this command here, it launched GNUplot. It gives GNUplot this command to execute. And then between the double quote, you have the entire GNUplot command. And then you redirect the result to a JPEG image. And so you don't open GNUplot, you don't do it interactively, it's just directly in one go. So that should work. That you can do. Right. So in my case, I leave GNUplot. Okay. Yes, so it should create an image. It should create this file. And now you can, with Jupyter Hub or whatever, you can list this, you can see this file on your Jupyter notebook somewhere. In my case, it should be here somewhere. Yeah, it's here, density.jpg. Right? And if I click on it, I see the JPEG image. Okay. And so what's great is that you can automate this if you want. You can make a loop and generate those images using a bash script in an automatic way, right? We're going to do this later. Okay. Great. So I think so anyone stuck like I was? No? Okay, great. So let's continue. Okay, so we have finished this. So now let's run a simulation by launching a parallel job. So as I said, what you need to do is to make sure that you load OpenMPI4, make clean, make ndim equal 2, MPI equal 1. We did that already. Now we're going to launch a parallel execution. Okay, so you must have seen this yesterday, how to do that, but let's do it. So here, basically, the key point that Ramses 2D is an MPI executable. And so MPI, just to summarize what it is, MPI, it's a library. So you need to compile the code with the MPI library. But MPI is also a runtime system. It's a system that also runs on the machine permanently and is listening whether someone is launching an MPI executable. And if the runtime system sees that there is an MPI executable being launched on the machine, it will put together a lot of communication protocols for this executable, and all the different executables that are running on all the different machines of your parallel system will talk together through the runtime system of MPI. That's why when you execute an MPI code, you have to execute it through the MPI launch command, which is in this case srun. S stands for Slurm. Slurm, it's an environment to launch parallel program. Okay? So if you do that, so here it will launch on 8 cores. So let me try to do it first, me alone, and then you can try to do it all together. So, okay, so you should be at the top directory, right? So here you see that you need to type, so srun -n8 means 8 core. Here I request 10 minutes, -t is the time, I request only 10 minutes. The less you request, the faster you will go through the system. Then the rest is the same as before, bin/Ramses2D and the name list. And for the name list, in this case, you need to use sedof2D, which contains all the parameters for sedof explosion. For those of you who know what it is, if you have seen Oppenheimer, sedof explosion as a nuclear bomb explosion. Yeah.
For some reason, it's saying I don't have the resources to do this.
Yes.
Oh, okay, let me try.
I have to put partition equals temp, and then it works.
Yes, so which partition?
Temp.
TEMP?
Yeah.
Okay, that's the partition that has been created for the school. So you have to add -p space temp. So in my case, I'm waiting. Right? I'm waiting, but at least it's not hopeless.
Does it matter where I put the P?
My brain was
That's
all
what
this
that's
stuff.
what -p seems to be working. That's what -p space.
Okay, now the job. Okay, now the job is running. You see?
srun dash. Sorry, this is dash
Okay, the floating point exception, it's fine. It means that there is an underflow, meaning that there is a number that was so small that the compiler or the Fortran cannot differentiate between 10 to minus 305 and 0. Right? But we don't care. Right? For us, it's the same thing. And so you can see that's the same thing as before, right? The level of refinement. So we have, it's 2D now. So it's a bigger simulation, you see. And here, this one is interesting. It's the minimum, maximum, and average number of grids per processor. So that now the problem, which is a sedof explosion, has been distributed among the 8 processors roughly equally, right? So that the program is running in parallel with an equal share of work among each processor, right? But it's not perfectly equal, right? But it's it's not bad. And again, you see that there is twice as many fine step than coarse step in this case. And the maximum resolution is 1024, but we have much less grids. Okay, so the new thing also is that we have created two new files, which are the output file, or the snapshots, as we call them. Output 1 contains the initial condition, and output 2 contains the final state of the simulation before it stops. Okay, so now we will try to visualize this snapshot. So let me, yeah, okay. So for this, we're going to use a tool which is in utils F90. So you go to this directory, utils F90, and here you type. So there is a lot of files here that we are not really interested in. You type make. In my case, it's done, but in your case, it should compile all these utilities. Okay, no problem, no weird error message. Okay, so now let's go back to the top directory, and now we're gonna use these two lines here. The first line will convert the snapshot number 2 into a map of the density field. And the second command will turn this map into an image that we're going to visualize. Okay, so if you do this first, okay, so this calls the executable AMR2 map that we just compiled. This tells you read output 2. This tells the code to output a map, and type 1 means the first variable, which is density. You can try with 2 and 3 and 4. You will get different maps, different variables. Okay, so it's processing. You see that there is one file per processor. That's the parallel computing kind of goodness, more files. And then it created the file dense.map. And that's in French, actually. Sorry for that. Okay, great. So you have this dense.map here. And now we're going to turn this map into an image using the second command, which now is a Python command. That's why you need to have Python loaded. And so this reads dense.map, the file we just created, and this outputs dense.png, which is a PNG image format. Yeah.
Sorry, I think we missed one of the steps. What was before this? Because I'm getting the error that there's no such file directory. So I think I was supposed to do make clean or something.
You need to do make in the util/F90.
You need to do make inside, yeah, in util/F90, you need to type make.
And then go back to directories. If that was
So this create the map. So in my case, it outputs the image. In your case, no. But it still creates dense.png, and you should be able to see it from your somewhere here. Yeah, here, this one. That's the map. Right? Okay. And so now you see that's the 2D simulation, obviously, right? So you see the shock wave, which is just touching the box, and you see the AMR cells here. You see how big they are here, right? And then when you approach the shock, it's very, very small. And actually, it's like 1 cell per pixel in this case. Okay. So that's the set-off exposure. Right? All right. So I guess you have run your first 2D simulation. Congratulations. With MPI. So, okay, where are we? So, okay, we did that. Okay, now we will submit a job, because now what we did was we use srun, which is more like, we submitted the job directly on the command line, right? But you can do better. You can submit a job script. Okay, so a script, it's again a program that contains some basic Linux command. So this is a Bash programming language, Bash. And basically all the instructions that you gave at the command line, in this long line, you can actually put them here as a list of sbatch command. Again, that's a slurm batch, right? S for slurm. And you can set how many CPU you want, number of nodes. Here I requested 1 minute. I can put a name. Then you have, of course, to module load OpenMPI4. You don't have to, but just in case you forgot to load OpenMPI4 when you connect to the machine, just put it in the job script so you know that it's fine. Right? Then here I have a trick that I put the date in this variable. You go to your Ramses directory. I don't know which one you use, and then you just put in the job script just this command, right? That we just did, but inside, and it will launch the job. Okay.
You also need to add a partition.
Of course, you need what is it called? --q equal temp. P equal temp. Yeah. --p equal temp.
That should be temp actually.
Give me.
One dash. Yeah. One dash space. One dash p space temp.
Yeah, like that. Right. -p temp. Okay. Okay. And then you submit the job by typing sbatch job.ch. I mean, this is inside the file that you can call it the name you want, right? I called it job.ch, but you can call it the name you want. And then sbatch. And so it will queue. It will wait some time before going through, and you can check what is the status by typing sq-u and then your name. Okay. Okay, so yep.
Is the squiggle in this case the same as
Home.
home?
Yeah, that's the same. The tilde is the same as home.
Where else does the mouse go?
/mnt. Oh yes. Yeah, these are small simulations, so it's fine, right? But once the simulation will become bigger, then we need to be careful. I will explain. Okay, and any problem with submitting the job? Say it again. Because you don't have access to temp. Have you tried -p temp? Temp.
Sometimes they call it. Yeah.
Export display. So you have to follow the steps that are described in the wiki. It's a bit annoying because it's complicated because you have to jump over a gateway and then on Rusty, and you have to make sure that it's all properly. But they explain how to do it. The easiest way is to change your .ssh/config file on your laptop and follow what the instruction they gave. So you have to copy a small paragraph into your .ssh/config, and it will automatically pass the display, and then you can do what I mean. It took me 2 years to get there. Now I'm bragging because I'm so proud I can do it.
Yeah, just added the sbatch.
Okay, so next step will be we'll try to make a movie. So in order to make a movie, as you know, we need a lot of image per second. So we need more snapshots. So So the way to do that, we're going to actually edit the name list file, sedov2d. Right, so you choose your favorite editor. You can also edit directly from the Jupyter Hub or the Jupyter Notebook. We'll click on the file, which is namelist sedov2d.nml. And then I can explain, by the way, briefly, what's inside this file. Right, so it's basically you have some parameters organized in blocks, and each block is a certain type of parameter. Right? For example, AMR parameter control the AMR grid. So it says that the minimum level of refinement is 4. So it's going to fully refine up to level 4, which is 16 by 16 cells. Right? And then the maximum level will be level 10, which is 1024 by 1024 cells. The number of grids you need to allocate, that's for the memory. So you need to know how many grids, you need to guesstimate how many grids you're going to allocate. If you don't know, just put 1 million and it's big enough. Right? If it's too big, it's going to crash running out of memory. And that's the size in code units of your box. So you can make it whatever you want, 4, 10, whatever. But in this case, it's a unit box. Okay, then you have the boundary condition here, which are set here. So it's reflexive boundary condition, so wall. Then you have the initial condition. So here we have a square covering the entire domain, and we have a point, which is the explosion. And so you have the coordinates, the length, and then you see the density, velocity, pressure initially. And that controls the output. Right? So we have only one output at t equal 1. Right? So we're going to change that in a minute. Now this constrains the hydrosolver parameter, the good enough method. So here you can change, for example, the gamma of the gas, if you want. You can change slope type. So slope type, remember, it's 2 slopes, min mode and Munsen. Slope type equal 1 is min mode, the safe slope limiting strategy, a bit diffusive. If you put slope type equal 2, you're going to have Munsen, which is more aggressive, less diffusive, so better, but risky, a bit risky. Right? So, etc. So you have you can also specify the Riemann solver if you want here. You can put, so by default, I think it's Rouzanov or Lax-Friedrich, but you can change, you can put any Riemann solver you want. And for this, you have to go to the documentation, which is on the Bitbucket wiki. They explain everything. Then these are the refinement parameters. So it refines on the gradient of the pressure. So basically, you detect the shock. And it uses the conservative variable for the interpolation. That's kind of more complicated. And it interpolates linearly. So these are parameters that are explained in the wiki if you want to dive into the subtlety of it. So for the time being, we're going to just change the output frequency because we want to have a lot of images, right? So for this, just do what's explained here, right? So you're going to put t end equal 1 and delta t out equal 0.01. And this obviously will generate 100 images, 101 actually, because t equals 0 will be 1 and delta t out. Okay, so let me double check. Yeah, so you can save this. And now you can resubmit the job. And it will spit out 100 snapshots. And don't worry, those snapshots are not that big, so you won't kill your home directory, I hope. Otherwise, we'll have to move to the scratch tier. Right? Yeah. Okay.
I guess I've only ever used Athena, and sometimes after changing like the copy generator, you have to read the file, but I don't know how name files work, so I guess it's different. You don't have to.
Yes and no. So I can explain. So basically the question for those of you who are in the back, there is some difference with Athena because Athena is using a problem generator. So here there is actually a default initial condition generator, Ramses, which is very simple. So that you don't have a problem generator or you don't have a problem to generate. You use the default initial condition, which is based on this here, init param, right? So here you can set different regions, different types of regions, and using these tricks, you can do a lot of problems without a problem generator. You just use this kind of built-in default setup. For simple problems, yes. But now if you want to do more complicated problem, then Ramses used actually another terminology. It's not a problem generator. We call it a patch. Basically, you patch the code, right? And so the way you do it, I can show you. So there is this directory called patch, right? And this directory contains a whole bunch of problems, which are more complicated, right? So just for example, this one is a collapsing molecular cloud. So the initial condition is very complicated. It's a Bonner-Ebert sphere. So you know, this one insta contains Kelvin-Helmholtz and a Rebbe-Taylor instability with some. So you have a whole bunch of stuff, right? So for example, MHD, if you go into MHD, maybe that's what you're more familiar with. You have a dynamo, ABC dynamo. You have Alphen wave. AW means Alphen wave. Not easy. You have a magnetic loop test. You have the famous Orzactan test, right? You have the rotor problem. All these are classical MHD tests, and they're all in those patch. So now, how do you compile the patch? Very easy. Let me show you example. So you go to bin, make clean, of course. Then make ndim equal 2, MPI equal 1. And now the problem. Patch equal / patch insta. Forgot what's inside insta though. So let me check. Exactly. So here you see you have the problem generator, which is this file that is actually modified from the default version of the file. And so you just have to indicate the path of the patch, and the makefile, the compiler, will look first where this file is in your patch, and if it doesn't find it, it will use the default value. And you see here that we only modified one file in Ramses, but other patches are much more complicated. Right, so for example, let me show you another very complicated patch, which is this one, which is the galaxy formation patch. Right, it has like 6 files, right, modified. And so what's interesting is that you can modify the code, you can break it, you can do whatever you want, as long as you are inside this patch directory, you're fine. Right? Okay, and so if you compile, then it will recompile everything, but using all the normal files, the same file as before, except for one file, in this case, conditioning.f90, that it will use the one in the patch. And this one contains much more complicated initial conditions.
And that's where you would modify the setup.
Exactly.
Oh, cool.
So it's a bit like the problem setup of Athena, right?
Yeah.
So I don't know. I think we just saw it. It's hard to see, but it's somewhere here, right? No, maybe later. Anyway, and now we have now this new executable Ramses 2D now contains a different initial condition, contains the Rebbe-Taylor instability kind of. Okay, so now let's crap. So now I break my. Thank you. Huh? So now I have to do it again. There we go. So now we have changed the name list for set of 2D with way more outputs. So now you can submit the job and it generates 100 outputs. Are you there? No problem? No overflow in your disk? No, it's fine. Okay, great. So now you can actually, you should see 100 outputs. So now what I suggest you do is you put in a file that you call movie.sh, you put this bash script here. So what it does, so this is bash programming at its best, right? So basically you do a loop where all the loop element will be an output directory. And then you just use the two, so we basically make a map, you make a map, and then you use this gnuplot command we just used to generate an image. Be careful because it's bigger, right? You need to really go to the right, right? You see, it's a very long line. Okay. So this creates the image. And then you're done, the loop is finished. And now you have to use this magic command, convert, which turn your all those images into a movie, right? A GIF animated. And then you clean what you did. And so in principle, you should see this movie. Yeah, it works. Convert works, or because it's always a bit fishy. It works. Great.
I think I need to compile AMR.
Yes, you need to go to utils F90 and then make. Yeah. And so now you see the movie of the set-off explosion. Okay. All right. So for those of you who are finished now, you can try to make your first 3D simulation, but this is totally optional. But for this, be careful. You really have to go to the safe scratch dir, as we call it. That's where you can have a lot of big data, and there is no risk of overflowing the home directory memory. And so, what I suggest you do is you basically copy this 3D now. So it's a set-off explosion, but in 3D. You copy this. It's a relatively small simulation. It's a 64 cube simulation, so it should be fast. No, it's a 128 cube simulation. So 2 million cells. It's pretty good. And you can launch it using srun. And then once you're done with this 3D simulation, it should be fast. It should be very, very fast because what did I do here in terms of, yeah, you see the output time is really small. So it's going to output after a few steps, right? So don't worry, it's going to be a fast simulation. And then you can use YT, the YT package, which is a visualization package working with Python to visualize the 3D data. Okay, so I think you can just do this for the next 20 minutes if you have time. Otherwise, take a break. I'll do it later. But that's it, we're done.
Okay, so I guess I'll just get started here. So I also have, that was Ramses. I will do something similar in Athena++, and I will zoom through kind of the basics of cluster things and modules, because presumably we've all got that down, but there are commands in here you can just copy and paste. So everyone should have gotten an email today that had a link to a GitHub page that has honestly just 2 files, and this is just a way to distribute these 2 files. One is just a bash script with comments, and that's kind of the tutorial instructions. And again, feel free, zoom through it as fast as you want, or as slow as you want. I guess I'll just kind of go through it at some minimum pace. On the other thing, this OT base.bash is a Slurm script. So you'll need that later when we run something in parallel. So people have got that, right? Good. Okay, so the way I kind of test ran this on the cluster is through this Jupyter Hub. I actually had 2 terminals and 1 IPython notebook. One terminal, just to get started, is where I'll do most of everything, compiling code, running code, and so on. I did a separate terminal for calling Python scripts to visualize things because if any of you have used clusters extensively, you find out that very quickly that often the modules conflict with each other, and like the environment you need to run Python is not the environment you need to run your code. And my first attempt at this, that was true. So I just switch back and forth. When I'm calling visualization scripts, I'll just go into a different window with different parameters. But just to get started, so through the hub, right, if you scroll down to the bottom, just choose terminal. So you should be somewhere on Rusty. And the first step is just setting up an environment. So here, these 3 lines that are not commented, right? These are just the environment I use on Rusty. Since I'm local here, actually, I use Rusty all the time. And these are things that I would use if I'm actually running Athena on this cluster for large scale things. So you can paste all of those in. And if you get any error messages, let me know. The first line is the important one. This is loading an up-to-date GCC MPI, the same MPI for Roman just used, and an HDF5 library. These other 2 ones are magic specific to this cluster. Don't try them on any other cluster. You'll also find if you use clusters that every cluster has its own set of magic commands to make things work better. That's just the way things are. So get to know the sysadmins and get on their good side, and they'll tell you like, this is the line you need to make your code run faster. These are probably not necessary for what we're doing today, but I just put them everywhere anyway. So that's our environment. So you can actually just test this big enough, by the way, or should I maybe try to zoom in a little bit?
So Chris, are you on Rusty or no?
Yes, so it should be, does this look like Rusty for everyone?
Do you, I don't know.
So I'm doing it through Jupyter Hub, right? You can just pick, yeah, you don't need to SSH from a terminal. I mean, if you want to, you could also do this SSHing through a terminal. At some point, this is just, it's easier to be here somehow, so you can double click images and they'll just appear rather than like trying to get them to your machine.
I don't even think it would let me do like a module load when I tried to SSH, so I switched over to the Jupyter.
Okay, so Jupyter works for everyone who's tried it, and SSH is kind of dodgy right now. Yeah.
But we can also SSH into Rusty from
No, sometimes.
our
you can
username
profile, so you can access
worker.
your home directory.
Oh, okay. Sorry. So yes, sorry. So when this worker node, this means that it is already underneath the hood. Jupyter automatically launches your job on a compute node, which you're not supposed to be able to access unless you yourself are running code there. And this number will be different for everyone, right? And this is just some random thing that was allocated.
That's my guess.
SSH Rusty here.
Oh, from here,
Yeah,
Yeah.
it works.
from this window.
Yeah, it works for me.
Yeah, for some reason we've been doing.
Yeah. You're just
Yeah, you're just
Rusty from Rusty.
Yeah. So now I'm 2 levels deep on Rusty.
Yeah.
It's not. Yeah. This isn't going to help you, I think. So you can, if you did that, you can log out from one of them, and then you're.
I'm learning so much.
Yeah, if you see just at worker, that means you're already there. You're on one of the worker nodes. The ones are set aside so every one of you can have like 10 cores to yourself. Yeah, the other Rusty was the login node, so everyone in the building's logged in there. And if everyone started running code there, it might get a little slow.
It's like a router, like you first go to the lobby.
Yeah.
Okay, so now we're on at least one Rusty. You can. So there was this question, it was mentioned yesterday, right, that there's different places to put files. So this is just a general lesson, right? Every cluster has its own preferences for where you put different things. Sometimes you might have up to 3 different places, like one place for source code, one place for like working directory for a project, and one place for like large files. So I'll put everything in one place, but here I'll do it on Ceph, which is the name of the hard drive, the file system for large files here. So you can CD into ~/Ceph, and that's just a shortcut. If you pwd, you can see like it has some address, right? And this is this Ceph is our local, you can do like parallel IO of, terabyte files onto this system. Not that we'll do that today, but I can just put everything here and be safe. Following along, so just as, right, Ramses, you do a git clone. So here we'll do a git clone. There's a last argument here. I just renamed the directory to Athena tutorial, whatever, you can call it whatever you want, but to be consistent with this, so I've already done it on this computer. If you do it, you probably shouldn't get an error message, right? So everyone, and the cloning should take like 3 seconds or so. And then we can go into that directory. So everything I do here this afternoon will be contained within this directory. So you can, and then I guess you can copy it out before all of your files are deleted if you really want to save it. So all right, so that's in the last setup thing. Okay, we've got the code. So the next step is configuring. So just as with Ramses, right, there was this, you can edit the make file, or you could, when you said make, you could issue commands like how many dimensions or whatever. Athena wraps that up in one other step. So there's a configure.py file. So you can look at that file with your favorite editor, Nano, Vim, Emacs, whatever. Whoops. Configure.py, right? And it has some help message, and then it's a bunch of junk that makes the code configure into the right thing. You don't need to understand it all, assuming it all works. The point is, though, whenever you're running Athena, the first thing you do is you set up these compile time parameters with this script, so you can just do. I'm jumping ahead. Well, you can always do configure.py-h, and it will just print out all your options for the code that need to be decided before you compile anything. And there are a lot of them. Mostly it's what physics and what coordinate systems you're using, and if you're running in parallel. So that's Athena and how Athena works. So I think the best way to get your hands dirty with the code is just to dive right into it. So here, I'm going to run through a shock tube example. So we're going to need to configure it, compile it, and then run it. And those are the 3 steps always. So if I just copy that line, this configure.py. So here you can see, what is Athena doing? It's setting a problem. There's a shock tube. So Athena always needs you to specify something that you're doing. There's no default here. So it's a shock tube. We're doing it in Cartesian coordinates. That's a default. I didn't need to say it. We're using the HLLC Riemann solver. If you remember Riemann solvers, an adiabatic equation of state, right? A gamma law equation of state, basically. And there is mention of ghost cells. Here, I'm just going to say that there are 3 ghost cells. So you don't need to worry about, that'll be good enough for all of our purposes for this example. So if you type that in, so if you type that into your Rusty terminal, you should get this output where it just summarizes all the options you chose. You can glance over it and say, okay, that looks kind of like what I thought I was going to do. Most of the physics is turned off. And then you can make clean. Again, this is just cleaning up your directory in case there's old junk there. Removes all these object files. And then you can just type make. Unfortunately, on this machine, I don't know, the make takes forever. There's a question about parallelization. Athena, you can definitely do make-j and however many cores you have. So if you logged into like 6 cores for some reason in this terminal, which probably you didn't, you could do that. I think there's also a question, if you ever run things often for production code, if you've never tried it, I suggest trying the Intel compiler over GCC. It's usually like 20% faster, the executable. But the Intel compiler takes at least 5 minutes in the last linking stage to like optimize your code in secret and fancy ways. Anyway, while that's compiling, so you'll need the window open for a second. So I'm just going to put everything into like a new subdirectory here. So again, I'm keeping kind of the source code and the outputs. Everything is all in one place that may or may not seem tidy. So everyone is somewhere in this stage. It's compiling. It's just going through all the hundreds of source files. if the code supports Intel, I think it's a good thing to try that. In my experience, Intel versus GCC, Intel executables are always faster. GCC is probably the least likely compiler to have bugs, and it always has the most advanced features, but it's also like, that's what they optimize for, and Intel optimized for speed above all else. I think when we wrote Athena++, we said like 10,000 lines of code, and now it's like 200,000 lines of code, and the compiler knows it. Okay, so I've at least finished. And again, you have very similar output. There's all the .o files, and they're all been linked together. So you can do this make dir tutorial shock, and that's just going to make some subdirectory where we can dump all the outputs without cluttering the main repository. And then you can move, so bin/Athena was this executable that was just created local to where you were, and let's just move it into this tutorial example. That way, if we recompile something, it won't overwrite that executable that we had. All right. So assuming everyone's compiled, so the next thing to do, so just like Ramses had this input file, Athena also has kind of its text-based input files, and there's a bunch that come with the code, and they're sorted in different things. They're all in this inputs directory. So if you can look at inputs, and they're kind of sorted roughly by physics. You might see there's a radiation subdirectory, and there's some input files for various radiation problems and so on. So for here, we're going to take this hydro athinput.sod example. I'll just copy it again into this new directory we made. So this is the sod shock tube. This is just the standard test. Whenever someone writes a hydro code, you have to it's almost a law. You have to put this figure in your paper to show that you solved this one shock tube test. And you can take a look. Yeah, let's take a look at it now. So if I look at this file I just copied, .athinput. So this is the structure. Okay, the first few lines are all a comment. That doesn't say anything. There's something here that gives you the name of the problem, like all the output files will be named. And then everything's organized in these blocks, right? So output 1, says, let's make some tab file outputs. And then we'll store the primitive variables as opposed to the conserved variables, and we'll do it every 0.01 time steps. You can also output a history file and so on. There's all sorts of controls. So there's the CFL number, 0.8. There is the integrator. So this is the second order Van Leer integrator. It's a second order in time algorithm. X order equals 2. This is the reconstruction and slope limiting algorithm that was talked about. So the 2 means we're choosing a second order thing, piecewise linear reconstruction with the Van Leer limiter, which is slightly different from the 2 that Roman talked about, but barely so. You can also check, probably the most important things for input files is, this is usually where codes specify resolution, right? So we're going to use a 256 cells in X and 1 cell in Y and Z. In other words, it's a 1D problem. Threading. Here's the adiabatic index is under hydro. And then there's all sorts of, this problem block gives kind of the inputs for setting up the standard shock tube. It says, the density and pressure and velocity and everything on the left and right in our initial conditions. So that's the structure of the input file. I think I suggested, just for making this match some future things, you can change the name of the problem to, let's call it the shock base. So it's the base case for the shock. And that'll match along with what I've been saying, and everything else we'll just leave as the default. So, yeah. So then you have your codes compiled, you have your input file. So to run Athena, all you do is you select the executable and you say -I and then give it the input file. The other thing you can do is -D and give it a directory, and it will dump all of your files in that directory, which is very convenient for not accidentally flooding the wrong directory with all the 10,000 outputs. So I'm going to put all the stuff in this subdirectory we just made and then run it. And hopefully this works for people. It ran, no errors.
Sorry, what did you just do? I meant that.
Oh, sorry. So I am on, in this file, I'm on step 5.
Okay.
Just copy that line and hit enter.
Great.
And it has, no one said it hasn't worked, right? You can scroll up.
No, you need to be on. Yeah, right. Do you find you ever have to lower the CFL number?
Yes. So actually, in multiple dimensions, depending on your time integrator, it might not be 1 that's the maximum. Like it might be a half or a third, depending on how people define it. And Athena defined. And also, yes, just for really hard problems, it's kind of an act of desperation. You say like, my code's crashing, maybe I'll just cut it in half.
Yeah.
It sometimes works. But if you get it down like to 0.1 and it's not working, you probably need to go back and change something. Okay, so people got this output? Yes, right? And so this is just it. Every time step is just telling you what time it was, how large the time step was, right? And it took 175 steps. And then it terminated because it said we got to however far you wanted to go. And it gives them summary statistics. This is kind of nice when you're doing a bunch of runs. You can see like quickly, okay, it used 2.3 hundredths of a second. And this was its kind of performance number and whatever. So you can, when you do multiple things, we'll compare these numbers as well. And that means, so now if we look, if you do ls and then this tutorial shock directory, you should see, actually I have more files in there than you probably do, but you should see a bunch of things that look like shockbase.block0.whatever, right? And those are, so we actually made 100 outputs from this code, or sorry, 25 outputs, more than we needed. So, okay, that ran the shock tube, and then the last question is, well, did it run the thing correctly? And so, of course, you do need to visualize things with all of these codes, right? So this is where you might be able to do this in the same terminal, but for my sanity, I'm just going to go to a file, new launcher, choose a second terminal, and then I will module load Python 3. And then in this case, right, so you can look at, here I have Python 3 loaded and all the defaults. And in the old case, right, I had this MPI and GCC and HDF5 libraries, and just in my experience, sometimes those don't, like sometimes you'll load Python 3 and it will unload your other modules. So I'll keep it in a separate tab here. So in this separate tab, make sure you're in the same directory as we were before. And then this mess of a line. So Athena comes equipped with a bunch of Python scripts that you can call from the command line that will just produce outputs. It's sometimes easier than like loading up matplotlib, loading in the data, and then like playing around with parameters to actually get, like, you just want to make a plot, right? Sometimes and see if your data looks good. So here there's this plot lines file, and it takes basically, we'll feed it one of the outputs from the code, and then we'll tell it to plot like 3 different values against X, and we'll make a PNG file out of it all. So if you just grab these 3 lines, there's other parameters, we tell it the left and right bounds and so on, just fancy adding in labels. And that, after a second, right, that should finish. And then if you check on the left, if you navigate, you should have a tutorial shock directory you can go into. And then, what did I call this? Yeah, and then if you double click the PNG file we've just made, this shock base init, hopefully it just shows up. this is the promise of high-level languages, right? It should just work, and sometimes it does. So has anyone gotten this plot to work? Yes, great. Okay, am I going too slow? Going too fast? Okay. So anyway, this is our initial conditions, by the way. So the standard shock tube, right? Density, pressure, velocity, they're all basic, or velocity is 0 everywhere, and we just have high density and pressure on the left and low density and pressure on the right. That's actually the initial conditions for this shock tube, right? And the idea is you had a tube of gas, and at time 0, you release it, and the gas is allowed to interact with the two sides. So that's our initial conditions. If the next line, step 7 on the file, is just the exact same thing, but I'm looking at output number 25, which is the last output, and I will make, let me go back to my terminal here. So I enter that, and I will make the final plot, and that should look familiar, because you've seen a lot of these over the last couple of days, right? And so this is at late times, density, pressure, and velocity for the standard problem, right? So yeah, we could do. Okay, so that's basic shock tube stuff. Slightly more advanced stuff. I think this might be, well, slightly more advanced. This will be kind of illustrative. So I have step 8. I said we're going to try. I'll go back to the first terminal here. I will copy this input file that we are using. I'll make 2 new copies of it. And then in your favorite editor, or you can, or by double clicking the thing on the left, I suppose. So if we go to the high resolution one, so the high resolution one, so now I'm going to set up something. I want to run at high resolution. What did I say? 1024 probably. Yeah, and 64. Okay, so 2 things I want to change in a file. I'll change the problem ID near the top. Instead of base, I'll just call it high. So again, this will make different names for the output files. Otherwise, you're just going to overwrite all your old data. And then if I scroll down, somewhere under mesh, right, this 256, and I don't know why it doesn't have my usual color scheme on, so you can't even see where my cursor is, but okay, there's 256. We'll just change it to 1024, and then you can save and exit that file. And then do the same thing for the slow one. Oh, sorry, not slow, low. Right, so we'll take the 256 and we'll just reduce it to 64 cells, and we'll rename shock base to shock low. And then we should be able to just run the same executable and just give it the different input files. So there's the high resolution run. And note, by the right, the high resolution run took 0.16 seconds, and you should do the low resolution, which completed in less than 100th of a second. That looking familiar? So far, the code hasn't, yeah.
Sorry, I'm just quite a little bit behind. What were the cell numbers for the high and low?
Oh yeah, so high, let's do 1024. I think I wrote it here. And low, let's do 64. So yeah, changing the resolution by a factor of 4. Okay. This time, actually, I did not write the full command in the script I sent, so it's on you to fill in the blanks, right? So, oh, sorry, I'm in the wrong. So if you go to wherever you were calling this Python script to plot lines, right? So we want to do the same thing, but instead of base, I want to plot lines for, let's say, the low resolution simulation, and I should probably output it to a different PNG. And you can do the same thing for the high resolution as well. And all is well. Let me close some of this. So you should have the final state at low resolution and the final state at high resolution. That's worked for some people. Yes. And you can toggle back and forth, and you can see now the difference, right? You know, at high resolution, this is 16 times the resolution. You get these very sharp shocks, and this is actually very close to the exact solution. And at low resolution, everything's a bit rounded off. And that's just the thing with finite volume methods, right? Any sort of shock or any sort of feature will require some number of cells to resolve. And so if you just have very coarse cells, the whole feature will be spread out across those cells. Great. So the last thing I want to do with shock tubes is, sometimes you can't just use the built-in script. You do have to load your data into something and actually manipulate it. So we'll try that in Python. So going back here, if you go to File, New Launcher, and this time we can pick the notebook. There should be this fluid we set up yesterday, right? So here's so in your IPython notebook, if I copy, let's see if this works now, this first block of lines into one cell and execute it. There's a real question. If that works, then everything else is going to work. Yes? Okay, yeah, so this is just changing into the same directory, and then we're going to import NumPy, and then we're going to, there's a Python module including with Athena. We just need to say to Python, look in this directory for modules, and it's called Athena read. And this is just how you get all your data into Python in some reasonably convenient form. All right, so again, we have a data equals sort of line. So if you copy that, so Athena read, we're going to call it on a tab file, and this is the final output from our base simulation, right? And that should just read it. And now data should be this dictionary. Actually, we can do, right? So data is this dictionary. It has maybe the time of the simulation, but also x1v, this is the x variable, and that has all your things, density, pressure, and your velocity in your three directions. And it's all NumPy arrays. So at this point, you can just do whatever you want, right? You can plot it, manipulate it, analyze it, publish a paper with it. It's all the same to me. People are comfortable with that? Nothing weird or strange? Okay. I'll just zoom right along. So that's enough of 1D. There's only really so much you can do with 1D in finite volume. Like honestly, if you have a 1D problem, you're probably doing like stellar evolution. You should be using Mesa or something, right, Jared? But 2D and 3D is where things get fun and pretty. So we can do a 2D example here. So I picked the Orszag-Tang vortex is just another standard. When people write MHD codes, they put a picture of this to show, look, my code can do the same thing everyone else can. So going back, we're going to need to recompile Athena because it's a different problem entirely. It will now have magnetic fields. And I'm also going to compile in this line, with MPI. So it'll be parallel distributed, and with HDF5. So this says, use the HDF5 library so we can make HDF5 outputs. And that's Athena's ++'s preferred method for parallel simulations. It's kind of the best format for that. So go back to one of your terminals, not the IPython notebook, and reconfigure. And now you should get this new output. And it says we have a new problem. Still, most of the physics is off, but some of these options have changed. And then, make clean. Again, it's a safety thing. And then just make. And yeah, this might take another minute. Yeah. Yeah. Oh, not just a stretch, not a question. Oh, there's a question there though.
I'm having trouble configuring, just doing like the running the configure.py thing. It just keeps getting me a bunch of errors.
Let's see. What does it look like?
It seems to be going. You are your modules loaded? You did your module list real quick. Okay, yeah. Your modules are not current. Window, try your other one.
Yeah. This is just my thinking.
Okay, and sometimes the
Oh, that's great. 14 different. You just figured out to do a dash H after it. Still be weird. Do which Python is it going to call the correct one that you think it is? Or and you can, is that the Python you want? You can do Python and then configure.py -h.
Oh, you're right.
No, that's not, that's not.
That seems like a good start.
Thank you.
Wait, oh.
Real good.
Keep it clean. There's no.
This also, I guess, this might also be some conflicts of like the Python with the MPI and HDF5 all in the same environment. So if you try it logging into a different window and just loading Python and not those, that might work. Okay, so this is hopefully finished compiling for most people. Yeah, everything I'm doing now, the compilation takes longer than running the code, unfortunately. Anyway, where were we? So all right, so step 12, all right, maybe I should finish step 11, right? So now we'll make a new tutorial directory just because this last one was getting really full of stuff. So what I call it, tutorial OT for the Orsak Tang vortex. So you could do that. And then any other steps? No, we'll just move the bin/Athena is this new executable, and we'll move it into the new directory. All right, so let's start doing 2D MHD problems. So let's grab, Athena comes with, again, there's a default input file that kind of is suitable for this problem. So we'll just make a copy of that, and then in your favorite editor, we'll look at this. Yeah. So we'll look at this base file. So again, I guess I made a few suggestions for changes. So we'll call it the OT base problem in preparation for higher ones. This file, by the way, comes set for VTK outputs. VTK is this weird proprietary format that works well in some cases, but I don't actually like it. And Athena is not really configured to do it optimally. So I'm going to take this VTK. Right before we had tab files, that's actually, you could have looked at those. Those are just text files. But when you do 2D and 3D problems, text files get very unwieldy very fast. So HDF5 is a nice binary format. I'm going to add in another phrase, ID equals prim. This will just name the files prim to remind us that they're primitives rather than giving them some random name. And then one last thing, XDMF equals 0. So has anyone used visit before? everyone, the people who've used it, have you liked Visit? No. If sometimes it's useful. I don't like it either. Sometimes though, if you have 3D data and you want to spin it around or do whatever, Visit doesn't read Athena's HDF5 files natively, but it will read the XDMF file that generates, and that will, so you can get it into Visit with this. If you're not using Visit, you can just turn off XDMF outputs and have less clutter on your file system.
Wait, does that like turn it off?
Yes, =0 turns it off. By default, it's on. And then, what did I say? We'll change it to 300, 150. So if you look for these NX1, NX2 parameters. So let's, for a starter, they start out at 500. So I said, let's change it to 300. And then 300 by 300 by 1, so it's a 2D problem. And then under this mesh block, this says, let's make it, what did I say, 150? So in Athena, mesh block is the name for a domain decomposition. So you have basically a block, in this case, 150 squared of cells, and that will function independently. So the whole grid is 300 by 300, but we're going to carve it up into 4 sections, and we'll have 4 subgrids in our domain. And this is how we can distribute this over 4 different cores, so it can be parallel, so it can be parallelized and run 4 times faster. So yeah, that's just Athena's name for that. The size of a subgrid is a mesh block. And let's see, did I say anything else be useful? No. Okay. So if you make those changes, we should be all set. But then, yeah. So then, instead of just running Athena from the command line, we're going to need to submit a Slurm job, just like you're doing with Ramses. So the other file in wherever I put that GitHub, right? This OT base. So copy that out however you can and put it into this tutorial OT directory. You could just open your text editor and copy the data into it. So otbase.bash. So this is the example Slurm script that I wrote. If you've seen enough of these, you start to see the patterns. Yeah, so, okay, let me just change, sorry. Your file will not have that line. Your file will look like that. So this, you set the partition. By the way, everyone will tell you all these 1-letter abbreviations in Slurm, like -p and -n, but then you do -n and -n, and you forget everything because like there's too many n's, right? Right. This is, and then you don't know what any. So Slurm always, you can put the full names and then keep yourself sane later. So we're going to run on just one node. We're going to run 4 separate processes. Put 4 of them in the node. This is redundant information. Only 1 CPU per task. If we were doing something like some hybrid MPI, OpenMP, then we could change this last one to something else. I'll run it for 5 minutes at most. And this just says, take whatever terminal output the code is writing and put it into this file. The way I structure things, I only ever want to modify the top of my Slurm file. So I modify these things as appropriate, and then the bottom kind of just takes care of itself. So, it's load those same modules I was using before just to be certain. And then there's this srun command where you say, look, I'm going to use this many CPUs per task, some magic lines, and then I'm just going to call Athena just as I was doing before. When you get on, every cluster will have its own variation on what this srun command looks like and what sort of magic you need to put there. So you just need to ask, the person who got you on the cluster, what do I run? So this is what it looks like on Rusty. So you shouldn't need to do anything with that as for the base run. And then, yeah, then you can just sbatch wherever we put this file, otbase.bash, and it should say submitted and it shouldn't have any errors. Is that working for at least one person? Great. And then you can do this thing, right? You could do sq --me, I think will always work for you. And it shows you all the things that are running on the cluster. One of them is probably this whole terminal and Jupyter thing is itself and it's been running for a while. And the other one is this OT base. And if you, all right, so now it's been running for 24 seconds. I think it takes about 40 seconds. Last time I timed it. You can keep doing this. You're really, do people know about the watch command? You can have the command repeat. Oh, so be careful with this. If you make it repeat a command every millisecond, the sysadmins will get mad at you because you'll be slowing down the thing. But you can do, what is it, Q or escape, Control C. Watch -N every so many seconds, and then give it the command you want it to repeat, and then you can just like watch things happen. I probably shouldn't have told you that. I'm going to get in so much trouble. Anyway, at some point, that thing should drop off. When you do SQ, it shouldn't be there anymore. And then you can take a look. Let's take a look at tutorial OT base.out, which is where I said dump all the stuff. If we look at the end of the file, so it ran 2,000 something time steps. It terminated at time 1, and it updated, however many, how big is this? 188 million cells were updated over the course of this thing. It took about 45 seconds and so on. So as people get, yes?
I'm getting an error that it was unable to create the file.
Unable to create, like a permission denied?
Like an HDF5 error. Yeah.
Oh, if you do module list, what does that show? Does it show something like this? In particular, does it have that HDF5? That's, has it worked for some people, or is everyone, okay, some people yes, and some people no. Okay, let's see what this cluster is up to. And you're submitting, So actually, someone who doesn't work for it, they see what this error is.
Yeah. You can, I was just gonna pull up to see what the error was.
Yeah, if you can.
I was being slow. Which one is it? OT base
Dot out.
Okay. What was the, I missed it. Oh, yeah, we can open it.
Oh yeah, let's open the whole.
And then the number of and then, but there's the application.
So it did run. It started.
Yeah, but maybe I did.
No, this would be consistent with running out of file space.
I think I've done that before.
Weirdly, because it. Yeah, it's somewhere on.
Yeah, I do that as well.
So because if you close out, if you ls that directory, you should see there's at least one HDF5 file. Like the initial conditions, I think, wrote out correctly.
Yeah. We don't.
Yeah, so it's just in the middle. That really looks like running out of space. Does this have a? Oh yeah, we're PWD. Yeah, and you didn't like download a terabyte of data when we weren't looking. So.
You know me. I like my data. I can compare. Maybe I skip a step or something.
I actually think you didn't do anything wrong. So
minus n and then
That's watch that and then the number of seconds. One. And then like your single.
okay.
Yeah, so can you try, if this didn't work for you, can you try these two commands? Module load fi-utils and then do fi-quota. The question is current near soft or hard limit?
No.
Not at all.
No.
None of, okay.
Are we the only two then?
Yeah, did anyone else have a problem with this, or is it okay? The cluster just picked two people and decided it didn't like you.
What is it? There was too much, they
Yeah.
reached the cap.
No, it looked like it, but they're not near the cap. But yeah, it ran for a few steps and produced some outputs and then started error messaging. Can you try, have you submitted the job a second time? Try it again. Yeah, that's something to be aware of. I've done that many times, though. I have filled up my quota, and often the error messages are very unhelpful.
Oh,
For these names.
For those of you who have finished, try step 15. If you copy those commands, you should get images of the final state of this. Is that, I see some nodding heads. That has worked. It looks good. It looks pretty.
Yeah.
Okay.
Looks cool with the magnetic field streamline.
Oh yes, yeah. So there's, if you see that note at the end of step 15, I say add these streamlines. So that will call matplotlib streamline function, and you can start seeing like the magnetic structure of the thing as well. What did I say? Oh, it should look like that, but maybe with the streamlines as well. Has it worked at all, or is it?
So for me, I think I ran the other time.
Okay.
I think it's running long enough.
Okay. Weirdly, I put things in the Slurm script that should take care of that, but sometimes it doesn't. Yeah. Okay, that's a. While the code's running, you can also always tail the output file and see the last thing that it's printed to file. For everything else, okay, so that was basic or Zegtang. Yeah, so I guess we can. All right, we can run. I did step 16 is running on, instead of 4, you can run it on 9 cores, and that should actually just run at 9/4 the speed approximately. We can do that. Have people jumped ahead and tried step 16? Did it work? Yes. So if you, whatever. So if you copy those, the input file and the Slurm script, and then modify them the way it says so, basically we're just going to change OT many, right? Right, so it was 300 by 300. Instead of breaking it up into 150 by 150, we could break it up into 100 by 100. So now we have a 3 by 3 grid of blocks tiling our domain.
Hypothetically, if you didn't be careful about making your mesh blocks and your number of requested actually line up,
then the code will give you an error. Yeah, so your blocks had better integerly divide things. That's something actually to be aware of too. With everyone has their own adaptive mesh refinement style. So Athena has the principle that you start with your blocks all at the same level, and then as needed you subdivide them, but they never overlap, and there's never like a high resolution and a low resolution in the same place. Other codes have different principles where they the low resolution is running everywhere, and certain places double up and do high resolution patches over that. So there's very different philosophies on what the best way to structure this is. I think this probably, the way we did it is like epsilon less efficient than other ways, but I think keeps us more sane when analyzing the outputs. But you'll hear things like block-based and patch-based and whatever AMR methods. So anyway, you can run, so if you copy those things and if you make those modifications the way it's described, yeah, so if I need .bash, right, and so I think, is it really laggy for other people editing files? Is that just me? Okay, it's other people too. Right, so I can run it on 9 and whatever. So if you make those modifications, you should be able to S-batch this thing, bash, and then just watch it, right? And then all right, while that's running, you can do the visualization. Spoiler alert, if you subdivide the domain differently, but like the physics and the actual grid are the same, it should get the same answer, right? That's kind of a test of a code's sanity, is it doesn't matter how you partition the work on 4 cores or 9 cores or whatever, you should hopefully get the same result. But I will skip to step 17 then, second to last thing. So this is just making a movie. So actually you were already introduced to FFmpeg. So if you want to do this, actually this might take a minute or two. So I gave these 3 lines, and this will, because for the base case, for the base case, we actually made 101 outputs. So we do this actually in the terminal that has Python loaded correctly. If I copy those lines, this basically loops through all 101. It'll print a little status thing as you're doing it, and it will just call this plotting script to plot I guess I did density here. So while it's doing that, well, you can just let it run for a bit. So then this is FFmpeg, right? So we can, wherever you are, you can do module load FFmpeg if it's not actually there yet. And then when you call FFmpeg, so there's, how many people have never used FFmpeg before? All right. Never or very little used it. Okay. Yeah, it's, for those who haven't, it has its own set of magic, and people pass down lore about what the best commands are for this. But it's the low level movie assembling script. Like almost every high level thing that creates movies calls this underneath the hood. But this, you can call it directly from the command line. So here I'm just saying, let's do 12 frames a second, every file that matches this pattern. This is a video encoder I chose because it's available on most systems. You could choose your own video encoder, and we'll make a movie out of it. But yeah, so there's all this nonsense here. And then I believe, all right, I don't know if, okay. This notebook will not just display .move files. Did it work for anyone? Or did you have to, has anyone copied the movie somewhere to actually view it? No, yeah. So I was hoping that I could just double click this and it would play the movie. Of course not. But if you SCP, right, if you look at,
Can you just rename the file or call it something else?
You would have to recall FFmpeg with a different extension. Yeah, and I guess the question is, if you have a favorite extension that FFmpeg recognizes and that this interface recognizes, then yes, that would work. I don't know which one that might be. Yeah, you can try MP4. I think this is just a wrapper for MP4 anyway. But anyway, if you grab, you can SCP, if you just go back to your home screen, right? If you can just, instead of SSHing to Rusty, right? If you, oh, that's really small. If you copy that movie to your computer, you can view it. I think I did. You can do this on your. All right, I did. This should be what you created. If FFmpeg ran correctly, this is honestly what you got. So that's just the time lapse of this problem. So this gives you some idea, right? People like this. It's this nice, pretty symmetric structure, and there's magnetic fields and everything. So that is what the Orszag-Tang vortex looks like. And I think for the last step, so yeah, let's just, okay, it finally worked for me. So that's, yeah, that's fun with movies. So the last thing I think is AMR. So this is good to get experience with this. Honestly, it's becoming less and less common that you can run finite volume codes without adaptive mesh refinement. These days, everyone's running these big things, and you really want to focus on one region, but you also need some other junk happening around it. So it's good to get a handle on the kind of art of AMR. So I just made a copy of the input file. And then, so I made an AMR.ath input file. And what did I say? I said, we'll change. Change the name to AMR so we don't overwrite our own files. And I said, let's do 180/30. That sounds good. So I said, let's, instead of 300 by 300, we'll start with a coarse grid, 180 by 180. And then, wow, it's really laggy. Okay. And then the mesh block will make 30 by 30, right? So it fits in, but we'll give it plenty of room. Basically, the idea is you want to refine, when Athena refines a region, it takes a whole mesh block and cuts it up into 4 pieces. So if your mesh blocks were really big and it decided, oh, I need to refine a little point there, that it would have to refine the entire thing, right? So for AMR, you kind of like to have nice small blocks. So kind of just look locally and say, okay, there's a little bit of something I need to resolve. So I'll refine that region, but I won't throw resolution everywhere on the grid all at once. All right, and then there's also, we need some extra parameters that are not even listed here. So if we add a refinement equals adaptive right under this num threads, for instance, and derefine count equals 5. So derefine count says, don't, even if you think you can coarse in a region, because the interesting physics has passed along, wait 5 time steps before doing it, because maybe something will change, right? You don't want to, with AMR, there's a risk that you keep changing your mind, you refine a region, then you de-refine it the next step, and you refine it, and there's a lot of overhead to that. So you kind of want to avoid that. And num level equals 3. This basically says, go 2 levels beyond root, right? You have to put a limit. If this goes up to like 20, you'd end up refining down to the atomic scale. Your code would take forever to run. So we set it, so that's just the limit on how far down it can refine. And then finally, I'm going to add, somewhere in this, I'll just put it at the bottom, I add a new block called problem. You can call it actually anything as long as it's consistent with the next steps. And I said, let's put 2 new parameters. And so in Athena, you can read in extra data. You can just put anything you want in this input file, and then there's a method for actually reading it into the code and doing whatever you want with it. So I just put these 2 new numbers here, and this makes it easy to change these numbers later on. And you should be able to, I won't guarantee that all Hydro codes can do this, but most of them probably have some methodology for that. So you can just make your own parameters and read them in. The other thing we're going to do is change this this OT AMR.bash. Right, and you get something that I just said to basically rename the input file, or sorry, rename the executable. We're gonna have to recompile Athena. So, like did I say we're gonna recompile? Oh yeah, and we'll need to recompile because in order to run AMR, this was a problem that didn't know about AMR to begin with. So we're gonna have to write a little bit of C++ code to get everything to work. That should be fine. So I'm running out of time and I don't want to go any minute past 5. So the instructions are here. So I will just show actually kind of the result of what this looks like. So if you go into source pgen, if you follow the instructions, basically you will make a new file, this orseg-tang AMR. So this source pgen directory is where Athena keeps all its problem generators, just like Ramses had its place. You can just make new files here. It's good to start from one that exists, right? And there's already been a lot of junk in here. There's headers, whatever. But basically, one thing you do is you add. We're going to add a function declaration, this refinement condition. And we're going to add a couple variables. I enclosed it in a namespace that's, in some cases, it's good coding practice, so it doesn't introduce a global variable everywhere into the code. And then there's this function, so Athena has this init user mesh data. This is something that runs at the very beginning of the code. It's kind of an extra setup function. And it's saying, when adaptive mesh refinement is turned on, read in those 2 variables that we set in the input file. Right, this is how you can read in any variable you want into the code. And also just enroll this function that we're going to define. The code has to call when it decides, should I refine or de-refine a block of cells? And all the interesting stuff happens in that function. So here's the function I wrote, and it's a very simple, well, 7 lines inside a loop, but it's actually, it's more verbose than complex. So what it does is it's going to loop in 2D through all of the cells. So it's using indices I and j. It will then look at the density field, and it will construct this kind of Laplacian quantity. So it's, value at I plus 1 minus twice the value at I plus the value at I minus 1. So this is exactly what you get when you take a second derivative numerically. It'll do it in the 2 dimensions, and it will basically just sum up the absolute values of this. And it will do the same in pressure as well, and it will just store the largest value of this numerical Laplacian that we're taking. The idea is after it exits the loop, it will say, is the curvature of these quantities the maximum curvature I see in this block of cells? Is it above a limit where I should refine, or is it below a limit where there's nothing interesting happening so I can actually coarsen the grid? Or is it, it's in between those 2 points? So if the lag, whatever stuff, return 0. So this is just, this function has to return 1, -1, or 0, depending on whatever it wants to look at. So here I did this Laplacian. Gradients are another common thing to look at for adaptive mesh refinement. Basically, you want to see where things are changing fast. You probably should focus your attention, but this is very much an art. So it depends on your problem, and getting AMR right usually takes a few tries. That's just the way of it. You do something and it will over refine or under refine, and you're like, okay, maybe I'll run that again now that I know what it's actually going to do. So all of this was just instructing on how to put that into the file. Because we changed the source code, you will have to recompile Athena. I'm sorry if you do this on a machine where you have like 20 cores, feel free to run it in parallel. So people know about make.j, everyone? Maybe some knows, right? When you're doing make, if you do make-j20, it will spawn 20 threads and run about 20 times faster. If you do this on the login node on a cluster, they might get angry because they might have only 20 cores and you just like used all of them. So don't anger your sysadmins, or not, at least not too much. But that would speed up compilation. So I won't do it now, just to not take up too much time. So you go through the same process, configure it, we'll move the executable somewhere, and then sbatch this new tutorial, this new Slurm script as modified, as it describes with the modifications above. This I think takes about 4.5 minutes to run the last time I timed it. If it takes over 5 minutes, you might be kicked off. So you can then change the Slurm file to, how do I have an example of this here? You can change this time limit to be like 10 minutes or something. Yeah, by the way, here actually, and in some clusters, they're very generous and they let you run things for like a week. I recommend not doing that because one, there's almost certainly something will crash over the course of a week. But also, if your job's only going to take 10 minutes, tell the cluster it will only take 10 minutes, and then you can slip in ahead of someone while it's waiting for nodes to clear. That's how you get through the cluster much faster. So don't like leave it to the default of I'm going to claim these nodes for many days and I only want 10 minutes of it. Okay, so when you do that, you should be able to, so it'll run and it'll produce the same 100 outputs as well. You could stitch those together in a move if you want. I think the one thing I want to show, this plot slice script can also plot the refinement levels. So if you, it's in the wrong terminal. This gave up on file 73, it looks like. Oh, we finished there. So if you call this, instead of saying plot density, you could plot refinement levels. And what that should do is, I can bring up the image. So this is a color plot where teal means level 1, so it's refined one level beyond the original. The purple is the original refinement. The yellow is even higher refinement. So the idea is it found the regions that were interesting according to the Laplacian we wrote. And it sort of worked. I mean, some regions were left coarse. Not everything was refined at the highest level. So this is, you expect patterns like this. If you actually do the same thing for the last output file, I think I did that here, it's all yellow. So that means in this problem, our criterion said that everything was interesting, so please refine the whole grid, which is not ideal. But I think that the lesson here, though, is it really depends on the problem how useful this is. So here, this thing goes turbulent and everywhere does become interesting. If you had a problem where you're tracking like, a cooling gas cloud through a domain, hopefully you can choose refinement that just tracks that and doesn't refine everywhere. So this toy example was just a little, it works for a bit. It's not the best thing for AMR. But yeah, is there a question?
Can you pre-refine certain regions?
Yes, so in Athena, it has both static and adaptive mesh refinement. So I didn't show static, but if I, yeah, so what you can do is you can put these extra blocks in the input file. Let me just. Here. So if you say like, you can do things refinement equals adaptive, right, to turn it on, but then what it can also look for is a block that looks like this, where it says, make sure that everything bounded by these 6 surfaces between X, Y, and Z is at least refinement level 1 as soon as you start the code, and never let it go below that. So you can put as many of these as you want. So you could say, I want to find here and here and also over here, and then the code will self-consistently generate everything. So actually, in practice, depends what you do. Like if you do accretion disks like me, I almost never use adaptive mesh refinement. I use static because I know exactly where the disk is. It's in the midplane, right? If the disk isn't there, something went wrong. Yeah. Any other questions about AMR or Athena? I guess, yeah, it's not too much time left. So I put, you can, if you didn't finish this, you can finish any of these that you want at home. I also put suggestions. So I know some of you are using Athena. Is anyone using Athena that's not working with Yanfei? Are you all just, okay, there's at least,
Yes.
how many are using Athena because you're working with Yanfei? At least as many. Anyway, yeah, so if you have questions about Athena in general, I can try to answer them. Or if you have ideas for any, you want to try something in a code like this, you want to know what it looks like to add source terms or different coordinate systems. Athena loves spherical coordinates. You can contact me throughout the week or next week as well. I'll be around. I'm happy to help and provide guidance. We can also, whatever, we can find a place somewhere too. If you have like some burning question and you need an hour of Athena help, that's what we're here for. But yeah, other than that, I think I'll just leave it there. So hopefully you got some taste of finite volume methods and the things you can do with fluid dynamics. And I guess from here on, there will be other codes with very different approaches to get solving sometimes the same equations, sometimes different ones. And at the end of the day, you'll be able to choose what method works best for your problems. All right.